Yes. Hi, everyone, once again, and welcome to this course, Knowledge Representation and Management. So just to recapitulate, what are we talking about here? So that was my first question. So what was in the previous module? So what did we talk about?
Semantic web.
Semantic web. Yeah, what is it good for? It's not 8 a.m. Come on. Start your motors. So semantic web. Is there any use of this technology? Or what part of semantic web is still in use, rather, to ask? Okay, let's discover it. Let's do some recap. But before all, I want to say that this week is you should expect it rather intensive with respect to material. So we still talk about semantic web ontologies and reasoning, but on Wednesday I will introduce a topic of reasoning on ontologies. So today we'll talk about ontologies, and on Wednesday we will be talking about reasoning. And in the reasoning part, I will introduce you to the problem of neurosymbolic reasoning. Just kind of looking a little bit ahead, what is it all about? So you, in the first half of the course, you worked with logical agents, right? So you just completed the second lab where you made an agent finally to navigate the world using the knowledge base. And what's the catch there? So you separated the processing so from the knowledge representation. So the your engine is independent on the task. So it's really so your actions are modulated by the knowledge you insert in the knowledge base. So that's the whole idea of a reasoning agent, a software that that is not hard coded, basically. So the actions are not hard coded. Rather, for any action, it consults a knowledge base. And in the case of the first two labs, uses classical logics, predicate logic, to plan the actions. So that's what we do. And then we continued on onto knowledge representation, and again the red thread throughout the course is how to represent the knowledge and how to construct a reasoner. So the reasoner in the case of logical agents was well based on predicate logic. What we will talk about this week is a flavor of first order logic. But what is reasoner? So right now you have a kind of search algorithm. So you have a knowledge base where you it's kind of a database, right? A database of rules and facts. And you scan through this database, you find these rules and see the applicable ones. But all in all, it's you. I mean, I guess at this point you have this intuition of a database. But what about AI? So let's think about it. What is AI? What is I? I mean, intelligence. I mean, how do we do reasoning? Do we have a database inside the brain? Well, it's not a tricky question. I mean, we don't have a database. I mean, we have a brain, which a complex neural machinery that somehow help us to do this kind of inference, right? So true biological intelligent entities, like we humans, other animals, bees, honeybees, they do reasoning not by scanning any digitally represented data. And so aiming at creating AI systems that would be embodied or would, in the long run, be closer to biological intelligent systems. So one of the challenges is to create reasoning which functions on similar principles, based on similar principles. So what are those principles? Well, that's a problem. Nobody knows exactly. But there is an area of science which is called neurosymbolic reasoning. So you tried symbolic one. So basically, you have your rules, a set of symbols, so sentences constructed of symbols, and then you have these algorithms of processing it. So how to do similar things using interactions between neurons. So that's the challenge of neurosymbolic reasoning. And so on Wednesday, I will introduce the topic of neurosymbolic reasoning and focus on one specific flavor of it, which uses algebra of high-dimensional vector representation. So that's pretty much my research area, and apparently it is very compatible with what we are talking about today and tomorrow. So how to reason on ontologies using some neuronal principles. It's good if you would read this article before Wednesday. So it's not a big read, but it's quite technical with some formulas, and try to understand the concepts behind it, because this is something you will do as part of Lab 3 as well. So it is important that we do like several iterations. This is a new material, so I kind of upgraded this module this year. And it's important that we are on the same page, kind of, and maybe do several repetitions of this material. So first, I suggest you to read this. And on Wednesday, I will give you my version, so you have possibilities to ask questions. And then next week, you will do Lab 3. And Lab 3, so I will publish it, if not today, tomorrow. That's my ambition, because we do some final changes. It will consist of two parts. Part 1, classical ontologies. I will introduce what ontologies are. So I will introduce a tool on how to work with ontologies. So that's kind of an engineering approach to knowledge representation, management, and reasoning. Again, the symbolic part of it. And for part 1, so there is a tutorial, a rather lengthy document, like a step-by-step instructions on how to construct an ontology, your own ontology, and how to perform reasoning. So it's rather mechanical, and yes, but in part 2, you will take a tiny bit of these ontologies that you have created and try to implement it using methods described in this article. So, and for this lab, I will give you time. I will give you 2 weeks to implement. So I think it will be a little bit overwhelming to make everything in 1 week. So the deadline for this lab is in 2 weeks, starting from Monday. And of course, you will be assisted in Discord. But so as part of preparation, read this article, come on Wednesday, and ask questions, if any. But and I linked it in Canvas now. But now back to our business, and let's talk about this stuff. So let me see. What do you see in Zoom? Do you see my presentation mode or notes? You should see, I guess, presentation mode. See PowerPoint. Okay, good. So full screen PowerPoint. Okay. Good. Thank you. Now manage to move my mouse back to the screen. That would be great. Where is it? Here. Okay. So back to my initial question about the material of the last theory module. So we talked about something which is called resource description framework. So this is the main standard of semantic web. And it was created to what? Describe resources. Just formally annotate resources. And what are resources? Anything, any objects, physical objects, virtual objects, anything. So, and this is an XML implementation of a statement about a resource homepage and its creator. Okay. Then also we started as a kind of a short compact notation for RDF. So the main construct in a resource description framework is a triple, remember, subject, predicate, object. So, and a set of triples form a knowledge graph. So if you scan your, so you have a database with triples, you scan triples and kind of see the matching parts. So you can build a knowledge graph. I will show you graphically shortly. And apparently write it in XML form is quite tedious. So a compact notation called N3 was created. And so in N3, again, relevant to the context of this course, you can write, in a single sentence, you can write information about multiple triples. Again, a side note, N3 was created as an extension of RDF. So actually, it was created having some reasoning in mind. So RDF is not made for reasoning. It's made for annotating, describing resources. N3 was an attempt to create a language, so more expressive language, which allows to create some logical statements. There are some reasoners based on N3, but actually most straightforward most popular reasoners use or are based on other languages. For example, web ontology language that we will be talking about today. So again, why do we need to describe resources? In the context of AI, so we always want to make a connection of um, of a physical world to a digital world, and there are basically two main approaches. One, which is a bottom up, so when you start to kind of try to generalize your observations, like through its sensory system, and hopefully derive some concepts. So, for example, LLMs could be attributed to this kind of techniques. So by analyzing texts, so it kind of generalizes to concepts. So you can interact with such system on conceptual level, or a top-down. So basically, AI, which is driven by formalized human knowledge. So that's our focus, basically. And the main idea was to, I mean, in the beginning, it was very pragmatic. So by the time the Semantic Web Initiative started, so World Wide Web was already well developed, and there was a need to kind of automate the navigation and understanding the information which is described there. So to transition from kind of internet of or web of links, web of data to web of knowledge, basically. And in this respect, such concept as linked data appeared. So in the linked data, so you could basically formally describe the information presented in a digital form. For example, you could have formal description of Stockholm as well stored in certain database, and this database. So there are different frameworks for formally representing knowledge. So one that's we will be using for examples is called DBpedia. And DBpedia is a very large so-called multi-domain ontology. So still, I'm using this kind of keyword without giving proper definition of it. So live with it for now. But it's a knowledge base which is derived from the Wikipedia data, and so you can go to this Wikipedia and you can go to this DBpedia and use the naming which is stored there. So this is a format of URI that you can access names in DBpedia. And so there is a link to the corresponding URL on the Wikipedia for this data. So, and again, so the idea that you should have in your mind is that, so on the one hand, you have information which is kind of interfacing humans, so which who read and should understand. We need nice representation, and on the other hand, so we have more machine digestible description of same information. And there was so the final goal was to make a unified description, so which kind of suits both worlds, humans and machines. And so I just want to make a historic detour to a technology which actually um, is not widely used nowadays, but still exists in some cases, which is called resource description framework in attributes. So essentially, it's a fusion of RDF, description language, and HTML. So when you develop HTML code, so you would insert some RDF statements about objects. And the idea is, again, that you so on the one hand, so such a file would be parsed in a human readable format, and on the other hand, it can be parsed searching for RDF statements, and a knowledge graph would be extracted. So with respect to current usage, so it's still used in some places, some legacy places like museums, which still have some web pages with embedded semantic data. So for mainly for automated processing of this information. But there are other techniques which are currently used for data represent or knowledge representation or semantic annotation of information. So used in Google and such, which are, for example, JSON LD framework and others. So JSON basically de facto standard for a standard format for structured data. But again, so just to give you an idea of this vision, what is it? What RDFA was created for. So here is an example. So it's a it's an HTML frame, and about myself, saying that that I have a nickname for other people because of my affiliation and my position. So what you can do, so still you can play around with this technology. So you can go to this resource over here. And play around with it again if you're in the case you're interested. So if I just take if I take this text over here and paste it here. So here is the rendering of this text so it's HTML side, and at the same time so it could be understood by machines formally. So so this information can be mapped directly into some knowledge graph, so in a structured way. So, but as I said, so nowadays there are other standards using this. So I presented it more for coherence purposes. So how RDF was meant to work in a global semantic web context. So let's move on to the main topic of today. And talk about ontology. So what is ontology? Well, here is the definition. It's a formal, explicit specification of a shared conceptualization. So very sophisticated definition. But again, so I try to digest it from the functional point of view. The formal meaning that it is machine readable. Explicit specification is that somehow you need to extract the concepts, properties, axioms, and explicitly define the framework. Share it means that it means for interoperability. So once you create this machine readable specification, so you want that other people also use it for their purposes. And and hopefully, if you talk about not hopefully, but I mean it's very desirable that if you create a specification of a certain domain of interest to many people, so that all people agree on this specification. So if you specify, for example, medical knowledge, obviously it should be like unique specification that people agree on. And so all in all, you construct an abstract model of this domain. So think about it now. So we talked about resource description framework. So we can describe things and their properties, objects and their properties. Is it enough for conceptualizing a domain? What do you think is missing? In RDF. So just in the way, just in the fact that you can take any object and formally describe its properties. Think about it. We will come back to it soon. So I will come back to this question. Maybe as a hint to this discussion, so the intuition, when talking about ontology, the intuition you should have is a kind of empty questionnaire form. So this is an ontology. So when you fill in these forms, so you create an individual. But without this information, so this is an ontology. Without details, filled into these empty fields. This is an ontology. So any ontology, it introduces vocabulary. And any domain has its own vocabulary. So if you talk about medical domain autonomy, so you have plenty of terms. naming the different parts of body. But then on top of this definition, so you should specify meaning of terms. So, and again, here is a human readable form, but you want to conceptualize it somehow. And for example, that's the way kind of we are up to this moment more familiar with. So we have some standard ways for formally representing knowledge. We can define, we can have a language, or we can define syntaxes for defining atomic statements, for defining complex statements. We can have predicates and such. So, and well, here you can recognize, for example, a sentence in the first order logic. Yeah, and ontologies is all about it. So starting from definition of terms, being able to formally represent facts. So ontology elements. Now, if you think about it, again, if we talk about maybe this figure, autonomy. So we, in the body, we have functions. I mean, conceptual organs. Organs, and so they have certain hierarchy. They have properties. Properties, they have own hierarchy. So ontologies. Actually, about being able to represent hierarchies of concepts and hierarchies of properties. Then again, so if you think about the complexity of a particular domain, so you obviously have restrictions. So some properties can take values in a certain range, for example, and such. So concepts, on the other hand, so they can be included in different relations with respect to each other. So they can be related concepts like joint concepts, disjoint concepts. Concepts could be equal, etc. And then finally, so at the bottom, so we have individuals. So when you fill in the questionnaire with the details, so in terms of ontologies, we talk about instances or individuals. Then I think it's also useful to have this intuition about kind of multidimensional representation space. So you have a space where all your concepts live somehow, and creating an ontology is about structuring this space, the semantic space. So, for example, you can say that, okay, we have certain individual or individuals. They can be included, well, they're classes of resources, so they can belong to, well, here it's a functional class, but it can be a class of I don't know, just humans, for example. So same resources can belong to different to different categories, obviously. So like in this case, um, so both individuals can be both lawyers and doctors at the same time. At the same time, we have another domain, for example, vehicles, so with own individuals, so own properties, own classes, like personal car, trucks, whatever. And then we have properties, again, depending on the domain, so there can be different. And well, all in all, creating an ontology is to wire all these things together, basically formally, and be able uh, to decide on some generalization. So if if a knowledge is not explicitly present, to make it explicitly present. So and that is a part of which is called inference. So before going into the break, I want to maybe stop at formal definitions of ontologies. So there are two. So we will be talking about two different types of statements. Statements about concepts, so we will call them T-box, or okay, frankly speaking, I will not kind of maybe I will not use it very often in the lecture, but I mean you will see it in the other contexts. So T-box statements are conceptual statements, and A-box statements are statements about individuals. And here is a graphical illustration of how they interact with each other. And everything will be created, or will be described based on RDF format. So we will create this ontological description based on RDF format. But so let's go to a break, do some leg stretching, and then I want to come back to my question: why RDF is not sufficient for? In what sense it is not sufficient for creating ontologies? So let's take a short break. Well, I mean, it is probably hinted by this illustration over here. So we called all this lengthy, boring discussion about what ontology is. So concepts and hierarchy of concepts, uh, properties, hierarchy of properties, uh, restrictions on properties, and finally individuals. So what RDF does, it allows to make very, very simple statements about facts. So just kind of describe the reality. So there is no information in this statement, so this is a triple, RDF triple, about who these symbolic strings, or what these symbolic strings are, what does this symbolic string mean, and this doesn't allow us to kind of add semantics, to add generally any kind of generalization. So, for example, having a husband. So, I mean, now if you just read this statement, Mary has husband John. So we can also say that having a husband, so it makes these two people being spouses in English, right? So you can kind of nest the hierarchy quite a long way. And that is what I mean ontology. So RDF in itself is very, very limited. It's just a way to write simple statements. So what we want, we want to extend this RDF to begin with to start describing belongingness of these individuals to different classes and subclasses and such. And for doing this, there is a standard which is called RDFS. So the RDFS is what is kind of used in the knowledge representation world as a kind of as a means to create simplest ontologies. So RDFS stands for RDF schema. So what you can, this is what you can do with the RDFS. You kind of expand the entire hierarchy of the domain that allows finally to judge on the or to decide on the individuals. So let us do it in a kind of fast forward way. So we can say that, okay, Mary is a woman and belongs to class. Well, let me see if humans appear, people, no, not yet. So has husband, well, is a property. And a property itself is an object, so it has a domain on which it actions. So it actions on concepts of woman and man. Well, no, has husband is property of woman, and well, in this very case, it specifies the range as man. And here you see kind of belongingness to a different level of hierarchy. So it is subclass of a person, but then I mean you can all kind of branch it from a global notion of class or of concept, basically. And then again, so we can define a property which is another property. So we can define as many properties as we want, whose domain and range would be persons, and they all belong. You see, so here at the end we have like a generic end for properties. And we can specify the relation between the properties. So that's what ontologies are all about. But at the end, so you specify this graph as a set of RDF statements. So person is a class, so you can formally, you can visually match it. Woman class, man class, woman subclass of person, blah, 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 blah. Hmm? And again, this is a machine readable ontology. Now, what you can do again, and this is somehow a link to or a pre-taste of your home assignment that you will do during Christmas, New Year time. So this thing is actually pretty much digestible by LLMs. So instead of just writing a story, so you can try the other way around. I bet you didn't try it. In some cases, and as you will see in the home assignment, it helps in improving the quality of LLM output. So if I go to our beautiful chat, and I will copy it into here. So let's see what it tells us. So, well, first of all, it was very good. Well, it's obviously very good at parsing of everything. But what uh, I mean is that based on this description, so foundational models, so they can immediately extract meaning that they can apply for, well, even internal inferences. So it obviously it correctly identifies individuals and see what's happening here. Summary, yes, and then basically a natural language description of the fact that you created. So again, so not going into details what the OpenAI model does. This is rather irrelevant. For me, this is an example of this interoperability of like formal description of the man and interpretation by machines. And this is, of course, a very advanced interpreter of a kind. But we are interested in a different side of it. What we want to do, we want to make it usable. So remember, we talked about ontologies being shared. So if you agree on that stuff, so you should publish it somewhere, and that people can access it and integrate with their ontologies and perform different kinds of reasoning. So the reasoning, and interacting with ontologies, we will go through tomorrow. But today, what I want to show is that, so again, so this is our converter from last time. So if I now go to it and oh no, that's different thing. And copy this thing over here. So let it guess for the output. And if no, so here is the XML version of it. And again, so just to show you, maybe again, that you have some visual memory when doing quizzes. So these are the set of tools that you can use. Sorry. So you can go to validator, first and foremost. You can do the go to validator. Oops. And here you can take this thing and ask to visualize as triples and graphs. And let me see if I parse. So here is the thing. So I mean, whatever I showed you before. So again, this is knowledge graph parsable by the machine. So in the quiz, I will ask you to visualize a knowledge graph. So and you have to copy and paste the stuff into corresponding fields. So well, use these tools. But again, so I started with the fact that it should be shareable somehow. And so now I can take this XML file. So you see, it's kind of much processable by machine, and I want to publish it. How you publish it? Well, you publish it as a web service or a web page. Or a page accessible via web. So I have my own server. I will keep it for a couple of weeks open so that you can try these examples yourself. But in a way, it's so it's called D0034E. So just empty Apache server on Amazon Web Services. Why it is not? Come on. What's going on? Okay, this demonstration is not working somehow. But it's not critical, so I will double check what's going on. Let me see if I have. Okay, so it's alive, but why it is not accessible? Let me see if I can use. No, I don't want to go into it. ddns.net. It's not HTTPS, of course. Yeah, me. So it's HTTP server. And then ontologies. So I have quite some ontologies. I played around, as well as some, I mean, queries I will use tomorrow. What I did here, so I copied this little ontology about Mary and John being married into a file. Into file this one or example this one as well. So that looks more like this. So this is it, and now it is available on the web. So in principle, you can build an agent again, which requests this ontology, parse it, and performs certain queries on it. So this interaction, I included a couple of tools here. For example, one interesting visualizer could be this one. I checked, so all the links should work, I guess. Yeah, so it's already kind of retrieves the ontologies and visualize it. So if I will. So this is some ontology that well, their default ontology. So you need to include resource identifier. So where to get ontology for visualization. So I guess you can do it in one of the fields. I just cannot find it immediately. So, but what is happening? So this is a demonstration of like internet level interaction. So there is a service that, well, in this case, just visualizes a knowledge graph, and it first fetches the ontology which is located at some other source and does parsing of it, and then also can give you some other information. So if you want some nice visualization of graphs, so that's one of the tools. Okay. Speaking of interaction between ontologies, so that's a very important issue. So if in the context of linked data, we talked about DBpedia as a source of formal description of different digital resources. So you can, so for example, you build your description using the names, ontological description using the names from DBpedia. However, you should understand, so same objects can be described in different ontologies, so depending on serving different purposes. So, for example, there is another ontology which is called geonames, and it focuses more on geographic information about places. And it also has a record about Stockholm, so it's not written like this. And in principle, so as I said, these two ontologies, they capture different aspects of the same object. So what's but in practical cases, you want to use them together, or you can say that concepts and two ontologies are same. So to break this semantic wall, so to say. And in ontology language, there are such properties where you can join two ontologies, and you can say that, well, these two ontologies are same. And in this case, for example, you can perform a query on these two knowledge bases. On information which is present in both ontologies. Yes, and we will see some examples of queries tomorrow when talking about Sparkle, which is a query language. Again, relevant to lab 3. You will be working with a graphical tool for engineering ontologies. This is an open source stuff from Stanford. It is called Protege. If you go to this website over here, let's double check that it works. Yeah, so you can download for different platforms. Again, you can use any version which is above 5.5 for your purposes. So when you install, it's a Java-based, I think, program. So it looks like this, and I opened the same ontology now by open from URL. So I indicated URL, but you can open any local file. So you will work in the lab. You will be working with the local file and ontology file. So what you see here, you have same information, but now in an editable form. So you can actually, and that what you will do, you will create, well, in that case, pizza ontology from scratch by populating different concepts. So this is the top class. So we look at the classes. So it has person, man, woman. So has been defined, and then, for example, I can check here properties. So again, exactly as we defined, we have husband is a property, is a sub-property of spouse, and then finally individuals, individuals and their relations to each other. So this is a tool for engineering ontologies. In practice, I can tell that if you work with knowledge representation, and well, this profession is still pretty much acquired on the market. So, for example, I think I told you that part-time I'm working with Ericsson, and so we have knowledge engineers in the group I'm working who describe the demand of mobile networks. So starting from has a certain deployment in the country, region, down to description of equipment. So like switches, routers, how they interrelate, what parameters, properties, and such. And so this description, well, they do directly in RDF format, so in textual files. So I'm not sure if they use Protege or something like that, but so yeah, it is more kind of. But there are other integrated development environments as well. Yes. And in Protege, or Protege is designed for creating ontologies in something which is called OOL. OOL stands for Web Ontology Language. And it is an extension of RDFS schema, so it just more expressive. So I will list some features now, but if you kind of now look at in the retrospective, so we started with RDF, which is really basic stuff, just to describe facts. Then RDFS is more expressive, allows to define concepts and properties and hierarchy of this. All goes further. So it describes well, it's a language which allows to express rather complex logical statements and reason on these complex logical statements. Type of logic which is used by all is called description logic. Description logic, again, is a subclass of first order logic that we learned. So again, at this point, I want to say that everything what we learned so far is kind of interconnected, from the simplest classical logics to first order logic. to reasoning on a web scale in information, and all as a language to represent this logic. So here is the additional stuff in OL, which goes beyond capabilities of RDF schema. So OL allows to introduce range and domain, cardinality constraints, transitive inverse symmetrical properties. I will talk about it even very soon. Allows to define disjoint classes, so that so basically it gives you possibilities to express more aspects of a real world than RDFS can do. And as I said, so it's built on top of RDFS. So basically, it defines extra features in it. So back to our example. So that would be enhance it with some cosmetics typical to all, but otherwise, I mean, it's pretty much same syntax as we've seen before. All on one slide. So now please meet all. So I go further. So you will read it offline. The stuff you can use, and you will read in tutorial and use it in lab 3. So what you can do with OL, so you can create rather sophisticated descriptions of relations between different entities. So again, back to what inference is. Inference is in the case of web ontology language and semantic web technologies, is mainly about making implicit facts explicit. So having the knowledge base of some statements and ontological description, you can make new records, and that's what you will do. So peeking into this neurosymbolic part, so this scenario, the part of ontology will be very simple. So you have an instance of pizza. So this pizza you bought from Porsche pizzeria, and it is of type margarita. So this pizza is margarita. That's what you see on the menu. At the same time, again, so if you think in ontologies, so margarita is a class of pizza. There can be many pizzas, so margarita is a class of pizza. So this instance that you bought in the box is also a pizza then, right? So that's kind of very simple, but this is the reasoning. So when you buy margarita in a box, so the inference you can make that this is a pizza. It's not otherwise explicitly stated anywhere in the menu. No, yes, it's written. We have our pizzas, but but what is not written there is that pizza is a type of food. So you can infer that okay, margarita is a subclass of food, and therefore this pizza is also food. So this kind of stuff. And again, so this is the type of inference and reasoning you will do with ontologies. Again, this stuff what I'm showing you is more of capability. So it's not that you have to remember it, but I mean what you can do. So this is an N3 notation, as you see. So a record defining that red wine is a subclass of all things that have red color. So there's a class which is a subclass of, and here you have a restriction of anything that has color red. So at the end, again, I don't know if you feel it. On the one hand, you can go you can go and describe as complex relations as you can only imagine. So I mean, if you want to ontologically describe real world, it will be mind blowing. So I mean, with all this stuff. What is it what is in it for us is as engineers, we always work with domains. I mean, and domain has very restricted descriptions. So in many cases, we want to describe a domain with a finite number of classes, properties, and such. And the final goal is that if many people will do the description of their domains, then we probably can do some interesting inferences using this descriptions. So let me talk about one important terminology, partonymy or part whole hierarchy. So this is a fundamental concept of AI. So that is how we do generalization. So that is the meaning. I mean, if you talk to or if you read literature about machine learning, they use word generalization to something different in some different context. In their case, generalization is applying a model on some unseen data, and it should. So if you, for example, want to build the model classifying telephone, so you present, I don't know, Google, Samsung, etc., but not Apple. So when you present Apple and hopefully model tells that it's a mobile phone, so then that is called generalization of machine learning model. So here we mean more general definition of generalization. So you want to understand higher level concepts based on observation, and that is super difficult for AI systems. So even I mentioned it in the introductory part, so now we come kind of closer to it. These foundational models like ChatGPT and such, they obviously have traces of this type of generalization. When you prompt, so what certain thing consists of, so then it can tell. But the problem is that it's like it's unclear what part of model is responsible for this. So it's so it appears as emergent feature of a model, not something that is kind of fundamentally understood concept. And for us humans, so this is the fundamental building block that we can that we built our generalization for, partonymy. So we understand part whole generation. A little bit of boring terminology stuff in the context of knowledge representation, and so there is another term which is called taxonomy. So taxonomy is something different. So it's a hierarchy of classes. So partonymy is understanding parts of objects, basically. So soup, ingredients of soup. Person, member of community, and other stuff. Piece of cake. And as I said, it's super important in AI to in order to make non-trivial reasoning. So yeah, it would help. I mean, it works both ways towards generalization, but also deduction. So when you decide on an object just by understanding the parts. So if I see wheels and a frame, so then it's most likely bicycle. So fault propagations. This is typical um, uh, case, for example, in mobile networks. So understanding which parts responsible for what function, etc. So all as a language itself, it doesn't have specific primitives for this part of property. But um, what you can do, you decide taxonomy as object properties and characterization. So again, so you will figure it out when doing lab 3. But here is um, is an example. So you have an object property, and then you say so you define it as an object property, and then you define its characteristics. So so important characteristics are transitivity. This is what I told you on the example of this pizza. So understanding a class of some belongs to higher class, while belongs to a subclass. And all this you specify when writing an ontology of your domain and reasoners. So you again, so you understand. So the algorithms that navigate through your knowledge base will make implicit knowledge explicit. So it will materialize certain facts just by partial description. Sorry, I skip this limit maybe. See what I have, but I'm almost at the end here. Maybe yes, the last word. So there are different versions of OL. So there is a OL2 specification. So it's a standard language. So you can find this description on W3 in W3 community, and so a new version of it is even more expressive than a original OL. Linking back to previous parts of the course, OL and ontologies is a subclass of first order logic. So it is here an example. So you define a class of person, subclass. So student is a subclass of a person, and properties and restrictions. So read it here. So this corresponds to this logic sentence. So in the first order logic, as we have seen before. And as such, So you can imagine that the reasoners are also the types of decidability addressing algorithms. So that we started before. So if you can represent it in this way, then you can also transform it into conjunctive normal form. You can define a SAT problem on it, and do the inference in the way how we looked at it before. Another important thing is that it's not a full-blown first order logic. So it is restricted to a certain type of inferences, so to ensure decidability, so that all reasoning tasks have to be completed in finite time. And this is done by requirements on how how you can construct your knowledge base, how you describe the facts. So you cannot describe it in a kind of arbitrary manner. There is you need to adhere to all descriptions and so comply to the design paradigms of it, and which is collectively called the description logic. All right, that's it. So next time we will talk about practical construction of ontologies and querying ontologies. So using semantic query language, which is Sparkle. Widely used as of today. So whenever you come across need to work with ontologies, so you unavoidably need Sparkle. So that will be tomorrow. Any questions? All right.